Good evening. Thank you all for joining. We'll start the session in 2 minutes. Uh, have you all watched this week's week two videos on probability? If you have watched, can you put yes or not in the message? I will be going through the contents in the session, but it is good if you have already watched the video. So it will be like a revision and practice for you to solve the assignment question. Yeah, okay. So this week content is on probability. This session it covers some basics on probability and some practice questions, followed by a discussion on previous year assignment question. So, in the lecture, if you have seen, um, it starts with explaining probability. So the lecture starts with explaining probability as a mathematical framework uh, for representing uncertainty. And it says that we have multiple sources of uncertainty, such as, for example, when we have a pack of cards and we want to randomly take a card, there is always some uncertainty about which card you will get. So, in such cases, when we are when we are trying to predict something, there is this uncertainty, and in such cases, we can make use of probability. And another example that is mentioned in the lecture is about deterministic system. Yeah. So first is about this inherent randomness that is always there, and second is about deterministic system where all the laws are not random like, but there is some incomplete observability. So the professor talks about when we take any system, when we try to describe a macroscopic description of a system, we know what all rules govern that system, but then there are things that we are not sure. For example, the microscopic part of that system. and there is always some uncertainty about that path. So to model this is where another aspect of probability comes in. Another example that is mentioned in the video is about incomplete model. Like there is no randomness, there is complete data available, but then still you would not make use of the whole data, or you want to make a model that is computationally tractable. So in such cases, again, there is some sort of uncertainty or randomness that comes in. So these are some of the examples where uncertainty is there, and probability can be always used to explain those uncertainty in these kind of aspects. Now, why use probabilistic ideas in machine learning is it comes like it is about two things. One is to use probabilistic machine learning models, and another is to again use deterministic models, but then finally analyze the output from the deterministic model from a probabilistic perspective. That is, first one is to construct learning system that try to mimic human reasoning about uncertainty. Within the model, there is some probability built in. That is the probabilistic model part. And deterministic model, for example, when we take neural networks, it tells us how the input is related to output. So we will talk about neural networks in the fourth or fifth lecture. So now consider that neural network is kind of a function that maps input to output. Now, this output again can be analyzed probabilistically because the learning system, you can say the learning system is correct only half of the time. For example, there is an image of a cat. You are telling that the system will tell this is a image of a cat 60 percentage of time. So that is where the probabilistic analysis in deterministic system comes in. So these are places where ML can be used, probability can be used in ML applications. Then there is this discussion about two interpretation of what probability means. That is the frequentist approach and the Bayesian approach. So the frequentist approach, it depends on the proportion of events in an infinite sample space. So right now, you just have to remember that um, it's a way of objectively measuring probability. So for example, when we have a certain temperature on a day with a certain pressure value, and the weather is like it's a cloudy atmosphere, and in such cases in such cases in the past it has been observed that 60 percentage of the time when these conditions were there, it has rained. So it's based on some frequency of observation. Whereas in case of Bayesian approach, it's based on some degree of belief. That is, you have a certain certainty about an event, a degree of belief. So it's a subjective measure. It incorporates some prior belief, which are then updated based on some evidence. So this is the Bayesian approach and the frequentist approaches. So these are two different ways in which we explain or solve the problems in probability. But then the professor also explains that it doesn't matter what approach you use, but the mathematics of probability works the same way. So it doesn't matter whether you use Bayes theorem to solve something or some frequentist approach to solve something, but finally you get the same result. Then the lecture In the lecture, there is discussion on various definition, such as random experiment. So a random experiment is we do an experiment and it will result in some outcome each time. So even if we keep a coin exactly the same way in the thumb and toss it, we get different outcome every time. So sometimes you get head, sometimes you get tail. So the outcomes are random. So such experiments are called as random experiments where the outcomes are different every time. Then there is a definition on sample space. So sample spaces. As I told before, every time you toss a coin with the thumb, you get a different result in every toss. So what is that result? It can result in when I toss a coin, it can result in a head or a tail. So those are the outcomes of the random experiment, and that is what we call the sample space. So this is the set of all possible outcomes of a random experiment. So if I toss a coin, then it is the sample space consists of head and tail. Now, then random variable is discussed. So I'm trying to quickly go through the contents and then we will do some practice questions. So random variable is, for example, we can consider an experiment. Maybe we can consider a football game. So we may be interested in many aspect of this football game. We wanted to know how many goals were acquired and how many corner kicks were there and how many fouls were there. So we wanted to know some aspect of this game. And if we consider this entire football game as a random experiment, because every time you don't know what will happen, the outcomes are different every time, then each of this numerical result, for example, the number of goals or the number of corner kick, it will give a result, it will give some information about the outcome of the experiment. So these are examples of random variables. So as I was telling, when we consider football game, we want to get some information about the game. So the game here is the random experiment, and we want to know about some outcome of the game, which is maybe the number of goals. So this number of goal, which represents an outcome, that is called as a random variable. So any aspect, any outcome is represented by something called as a random variable. So when I toss a coin 5 times, I want to know how many heads I get. So that is one outcome that I want to see, or I want to see how many times I get two head. So such kind of outcomes in the random experiment is represented by this aspect called as random variable. So suppose in the experiment, when I toss a coin 5 times, I'm interested in finding the number of observed head. So this observed head can take, so I toss a coin 5 times. So I can either get all tail or I can get one head and then I can get two head. In the end, I can get all 5 head. In the end, I can get all 5 head. So here, if I represent x as a random variable, which I want to, so I want to look into the number of heads this experiment will outcome. So So x is the variable that represents the number of heads. Then x is giving us information about the outcome of experiment, and x can take what all value? It can take a value of 0 or 1 or 2, etc. up to 5, because I'm tossing the coin 5 times. I can get either no head or I can get all 5 head. So there is this possibility of this random variable taking a value of 0 to 5. So for each possible outcome where the number of head is 0 or number of head is 1 or number of head is 5, this random variable always assign a numerical value. So it associate an outcome to a numerical value. So that is what a random variable does. It assigns a numerical value to each of the outcome. So it is like a function from the sample space to real numbers. So this x is like a function from sample space to real number. So sample space is this set that contains no head, one head, etc. up to 5 heads. And this is given, or this is mapped to, each of this outcome is mapped to a random, a real number value. And this is what a random variable is. So it's a function from a sample space to real numbers. And usually this is denoted by a capital letter, and the range of a random variable is all the values it can take. So if I say that the random variable x represents the number of heads that I get when I toss a coin, then x can take values 0, 1, 2, 3, 4, and 5. So this is the range of the random variable. That is the range of values it can take. Okay. So then another important part is about probability distribution. So a probability distribution will tell us how likely is that a random variable takes a certain value. So for example, if this is a fair coin, so there is a 50 percentage chance that I get head and also a 50 percentage chance that I get tail. But if it is not a fair coin, it's a biased coin, and there is a chance that there is a 0.8 or 80 percentage chance that I get a head, and 20 percentage chance that there is like I get a tail. So uh, so there is so these are the states that are that the random variable can be in. So either it can be in states that are more likely to occur, or it can be in states that are less likely to occur. And this is modeled by something called as probability distribution. So, a probability distribution tells us how likely a random variable is to take each of the possible values. So, a random variable can take any value depending on what the sample space is. So, for example, if the sample space has 10 members, the random variable can take either like it can take, so if it is 0 to 10, 0 to 9, then it can take each of the state equally likely, or it can take a certain state with a higher chance than another state, or it can take a certain state with a very less chance. So it's like some of them might be less likely, some are more likely. So the probability distribution is what tells you how likely is each of these values. So this is how like this is why we have different probability distribution. Now we will come to, we'll just touch upon the different probability distributions as well. Now before going to the probability distribution, there is one important uh, thing to define, that is the types of random variable. We have uh, discrete and continuous RVs random variable. So we have two types. We have actually three types. So we have discrete random variable, we have continuous random variable. We can also have mixed types of random variable. Now, discrete is when we have a countable number of outcomes. And continuous is when we have an interval or a range that we are interested in. So we want to know about the outcome within a certain range. That is when continuous random variables are used. So in discrete random variable, we describe probability in terms of probability mass function, and in continuous random variable, we describe probability in terms of probability density function. Now, probability mass function, as Sir explains in the video, it's like a probability at a certain point, but the other one is like a distribution. It's an area under the curve. Sorry, area under a region. So it's a probability mass function is probability of a possible value of a random variable, and in case of continuous random variable, the probability density function is the probability of a certain range or a interval. Okay. Now, I will, so I hope so these are some basic things. I'll just ask a very simple question. You can post your answers in the chat. So, a fair coin is tossed twice. X is the number of heads. Find the range of X as well as the probability mass function. So a fair coin is tossed twice. Uh, X is the number of heads. So the outcome that we are interested in is to know the number of heads, and that is represented by this random variable X. So we want to find what is the range of X and also the probability mass function. So first we can start with the sample space. So, sorry. So the sample space is given by, so I toss the coin two times. So we get the possible outcomes are either I can get two head, one head, one tail, one head, or two tail. So this is the sample space. This is the possible outcomes that I can get. Now, how many heads are there? So here is 2, 1, 1, 0. Now, the set of all possible values that X can take, X is the number of heads, that is the range of X. So, that is given by 0, 1, and 2. So, the range of X is 0, 1, and 2. I hope that is clear. Now, coming to the probability mass function of X. So X represents the number of heads. Now X can take value 0, X can take value 1, X can take value 2. So for each outcome we have to find the probability mass function. So probability of x is equal to 0 is how many are there out of the 4 possible, how many are there without head? That is 1 tt, so it is 1 by 4. Probability of x is equal to 1. How many are there with one at least with one head? So that is 2 by 4. And probability of x is equal to 2. It is 1 by 4. So this is the probability mass function for the x, for the random variable x. Okay, I hope this is clear. Now, the domain is the set of all possible states of x. That is another definition that has been given. Yeah. Now, so this is probability mass function, which is for a discrete variable, where x take countable number of possible states or values. Now, in case of continuous random variable, it will have a range in the form of an interval, and instead of a mass function, there is a density function. So it will be like you have to find the area of the shaded region. So so suppose you want to find the amount of rainfall, if it is greater than 10 mm, or if it is between a certain range, then for example, as mentioned in the lecture video, like suppose if you want to find whether the amount of rainfall in a what is the probability that the rainfall in a region is between 10 mm and 20, then you find this integral of 10 to 20 with p of x into dx, which is the probability density function. So here we always look at an interval, but there we always look at a certain point. Now, coming to, so this is continuous random variable and discrete random variable. Next, so there are specific distributions that are used over and over and are given specific names. So, and behind each of this distribution, there is some random experiment. So each of this distribution is based on some random experiments that has been observed in the past. So this random experiment, it models some real life phenomena. Some of those distribution, I think you already know about all this. Few of those distributions are Bernoulli distribution, binomial distribution, geometric distribution, Poisson, etc. So I'll just quickly go through these distribution, because these are based on some real life random experiments. So so this can model some random experiments that happen in real life. So when phenomena like a certain when there is a phenomena with a certain behavior, and when we want to model this, we can make use of these distribution. So what I'm trying to say is, for example, when we take the first symbol distribution, the Bernoulli distribution, this models random experiments that have two possible outcomes. Sometimes it is referred to as a success or a failure, or in a coin toss, a head or a tail. So it is a Bernoulli random variable is a random variable that can take only two possible values. So there will be real life phenomenon where the experiment will have only two possible outcome, a success or a failure. And this when such experiment occur, you can model it using a certain distribution. And one such example is the Bernoulli distribution. So it is like it is associated with a certain event A, and if that certain event A occurs, then we say that the random variable is 1. If not, we will say that the random variable is 0. And this is modeled using a certain probability P for x is equal to 1 and like 1 minus p when x is equal to 0, because there are only two possible outcomes. And outcome x is equal to 1 can happen with a certain probability p, and outcome x is equal to 0 can happen with a certain probability 1 minus p. So this is one of the simplest distribution. Now we can extend this and we can describe about binomial distribution. So, in case of binomial distribution, again, the thing is you have a random experiment with two outcomes, but then you repeat this many number of times, n number of times, and an outcome A can happen with a certain probability P and cannot happen with a certain probability 1 minus P. Then such phenomena, they are explained using a binomial distribution. I think all of you might be knowing this formula of binomial distribution. So this models, for example, if I toss a coin n times and x is the total number of heads I observe, then x is a binomial variable with a parameter n and p. And P is the probability, and N is the number of trials that I do, and K is the number of heads that I observe. So when there are experiments or when there are real life things that you want that has similar characteristics to this, we use a binomial distribution. Now another example is another distribution is this geometric distribution. So suppose here what we are trying to um model is it can model what is the total number of failures before observing the first success. So, for example, when we have a coin, and suppose I have a coin, and the probability of getting a head is P. I toss this coin until I observe the first head. So, till I get first head, I keep on tossing the coin. So we define X as the total number of coin tosses in the experiment, and X then is said to have a geometrical distribution with parameter P. Then this is like repeating independent Bernoulli trials until observing the first success. So it is like P of X is equal to K is 1 minus P raised to k minus 1 into p. So p is the first success, the first head that I get. And before this, k minus 1 time I have failed in getting ahead. So this kind of shows the total number of failures before observing the first head. So this is how this kind of random experiments are modeled. So you want to model what is the total number of failures that I had to go through before getting the first head. So that is uh, before it was all tail. So that is 1 minus p. And I did k minus 1 times, so 1 minus p raised to k minus 1. And in the last kth trial, I got ahead, so it is p. So this is geometric distribution. Now another uh, commonly heard is the Poisson distribution. So here we want to count the occurrence of certain events in a certain interval of time. So here we want to count the occurrences of certain event in an interval of time. For example, you want to count the number of customers coming to a store between 9 a.m. and 10 a.m. And you have seen that on an average there are 15 customers usually this time. So then we can model X, which shows the number of random number of customers. So you want to model the number of customers that come between 9 a.m. and 10 a.m. And you have observed that on an average, based on some past data, you have observed that between this 9 a.m. and 10 a.m., there are usually around 15 customers. Then this occurrence of now or the number of customers that are coming between this 9 a.m. and 10 a.m. can be modeled using a probability distribution, and the distribution is explained as e raised to minus lambda into lambda raised to k by k factorial, where k is the value that x can take. So, so it can be any real number value, and lambda is the average number of customers that have been observed in the past. Then, so these are examples of uh, discrete random variable distributions. Now, when we come to continuous random variable, there are another set of distribution. Uh, for example, the Gaussian or the normal distribution. So a normal distribution is when when there is a random experiment and when the outcomes of the random experiments are they are continuous, and when we take the outcome and plot it, it will have a bell-shaped curve, uh, and also the values or the outcomes will cluster around a certain mean value. Then and is symmetric about the mean, then we say that this uh, random variable, it forms a or it follows a Gaussian distribution. Now, another example is the exponential distribution. So exponential is often used to model the time elapsed between the events. So a continuous random variable is said to have an exponential distribution with parameter lambda greater than 0. And the distribution is explained as e raised to lambda minus lambda x when x is greater than 0 and it is 0 otherwise. So this is another distribution that is used to model the continuous random variable, the time elapsed between certain events. Okay. So these are so far we have been discussing about only one variable, but then uh, there is always this joint probability distribution. So there will be so there are so in real life we are always interested in multiple variables. That is, we are always interested in random variables that are related to each other. So one example is that if we take a random family, we want to know the number of people in the family, what is the income in the family, and the age of the family members, etc. So there are multiple aspects that we want to know about, and there comes the joint probability distribution. So if I have two variables, two random variables, x and y, a joint probability distribution is represented as the value, small value x it can take, and the small y that y can take. Now, this is the joint probability distribution, and there is marginal probability function, which is when you keep, so when you have both x and y, when we keep, when we summate over the values of values of one variable to get the value of the other random variable, we say it is the marginal probability function. So this will contain information about one variable in a joint probability distribution. Then in the video, the professor talks about the sum rule and the product rule. So the sum rule is where this marginalizing of the probability comes into, or the marginal probability mass function. So that is you sum over. So if you have x and y, we sum over the values of y to find the marginal probability of x. Same in the same way, we sum over the marginal probability of x to find the, sorry, we sum over the probability of y x to find the marginal probability of y. So I'll show a few examples of whatever we have discussed so far. And another one is the product rule. So product rule is probability of x comma y is given by the probability of y given x into probability of x. And here the y given x is the conditional probability. Given that x has happened, what is the probability of y? That is the conditional probability P of y given x into x. So this is the product rule for joint probability distribution. So now we'll see some example questions. Yes, I'll start with some basics. So there are two events A and B, and suppose probability of A is 1 by 2, probability of B is 2 by 3, and probability of A union B is 5 by 6. Then find probability of A intersection B. So when we have studied Venn diagrams and all in the past, we have studied about A union B is equal to A plus B minus A intersection B. So the same thing applies here. So probability of A union B is probability of A plus probability of B minus probability of A intersection B. So what we have to find is this probability of A intersection B. So A intersection B is probability of A plus probability of B minus probability of A union B. And all of this are given. This is 1 by 2. This is 2 by 3. This is 5 by 6. Yeah, so you will get 1 by 3. Another question. So there is a machine, and this machine produces defective items with probability 0.05. And there is another machine, and it also produces defective items, and that has a probability of 0.08. So assume the machines are working independently. Question is, what is the probability that items from both machines are defective? So you have one item from machine A and another item from machine B. What is the probability that both the items are defective? Yeah, so we have studied that probability of A intersection B is probability of A into probability of B if A and B are independent. So here A is the machine A producing a defective item and B is the machine B producing a defective item. And the probability that machine A produces a defective item is 0.05 and B is 0.08. Now, when the probability that both are defective is A intersection B. So it is just 0.05 into 0.08, which is 0.004. Now, there is a random variable x, and it is a discrete random variable, and it has a certain probability mass function which is given like this. So it is 0.14 x is equal to 0.2 and 0.24 x is equal to zero point 0.4. It is 0.24 x is equal to zero point 0.5. It is 0.34 x is equal to zero point 0.8. 0.24 x is equal to 1 and 0 otherwise. So this is the probability mass function for this random variable x. The question is, find the probability of x less than or equal to 0.5. What is the probability that x is less than or equal to 0.5? That is, when x take any value less than or equal to 0.5, what is the probability? Yeah. So when x is less than or equal to 0.5, that means x can take 0.5, or x can take 0.4, or x can take 0.2 as per the values it can take. Now when x is 0.5, it is 0.2. When x is zero point 0.4, it is 0.2. When x is zero point 0.2, it is 0.1. So it is 0.5. I hope it is clear. Next question is, find probability of 0.25 less than x less than 0.75. Yeah, so it is 0.4. So it is probability of 0.4 plus probability of 0.5, which is 0.4. Okay. Now, so one question on independence. So there are two dice, and observe two numbers. So whatever the outcome in the die is represented by x and y. Now, what is the probability that x is equal to 2, y is equal to 6? So there are two dice. They are drawn independently, and whatever is the outcome is represented by x. So what is the probability that x is equal to 2 and y is equal to 6? Yeah, so it is 1 by 36 because these two dice, they are rolled independently. So to get probability of x is equal to 2, you get 1 by 6, and for y is equal to 6, again it is 1 by 6, so you get 1 by 36. Next question is, probability. What is the probability that x is greater than 3 given y is equal to 2? So it's on conditional probability. What is the probability that x is greater than 3 given y is equal to 2? Yeah, so this example has to do with the conditional independence explanation in the lecture video. So there is this portion where sir tells, so x and y, they are independent events. And in that case, if probability of x given y is asked, it is equal to probability of x. That is, it doesn't, x and y are independent. It doesn't, even if so whatever is the outcome of y, it is not going to affect x. So it is just equal to probability of x. So here, the two dice, they are thrown independently. So whatever value y get is not affected, like it's not having any impact on x. So this is just probability of x greater than 3. So that is when the die can take value 4, or die can take a value of 5, or a value of 6. And each of this is 1 by 6, 1 by 6, 1 by 6. So it is 3 by 6, which is 1 by 2. So this has to do on conditional independence. This is discussed in the lecture video. Another question is this kind. So there are sometimes questions asking at least one, the chance of getting at least one, such kind of question. So a man purchases a box of 75 decorative bulbs. If the probability that any light bulb is defective is 0.02, calculate the probability that at least one light bulb is defective in the box of 75. So a man purchases a box of 75 decorative bulb. If the probability that any light bulb is defective is 0.02, calculate the probability that there is at least one light bulb that is defective. So the probability of defective bulb is 0.02, and the probability of a non-defective bulb is 0.98, 1 minus defective bulb. So probability of at least one bulb defective is 1 minus probability of none of them defective. So it is 1 minus probability of all the 75 in the box are good, and a non-defective bulb has a probability of 0.98. So all the 75 are good. Then that is 0.98 raised to 75. Is around 0.7. Now I'll do one example question on joint probability. So there are two random variables, x and y. And it's given x can take value 0 and 1, and y can take value 1 and 2. And question is, the probability for each of this case is given 0.28. Question is, find the missing joint probability. What is the missing value here? Yeah, correct. So this uses the concept of total probability. So when you sum all of this, you should get a value of 1. So 0.12 plus 0.18 plus 0.28 plus this unknown value, let it be z, is equal to 1. The law of probability where the sum of the probability will be equal to 1. So then you can find this z and it will be around 0.42. Now the next question is, there are two random variables x and y, and x takes value 0 and 1 and y take value 1, 2 and 3. And the joint probability values are like this: 0.05, 0.20, 0.30, 0.20. First question is, find the marginal distribution of x. Find the marginal distribution of x. Yeah. So the marginal distribution is, for each value of x, we sum over the probability for different values of y. So for calculating the marginal distribution, p of x is equal to 0. We sum over the different values of y. So it is 0.10 plus 0.15 plus 0.05. Similarly, for probability of x is equal to 1, we sum over 0.20, 0.30, 0.20. Okay. Next question is, find p of x is equal to 1. Yeah, so it is just, so when x is equal to 1, y can take 1, 2, 3. So you use the sum rule to sum over the different values of y. So 0.20 plus 0.30 plus 0.20, which is equal to 0.7. What is probability of x is equal to 1, y is equal to 3? Yeah. So you can write it directly from the table. It is 0.2. So it's just to make sure the joint probability concept is clear. Um, Next question is, so there are two events, A and B, such that probability of A is 0.6, probability of B given A is 0.5, probability of B given A complement is 0.2. Find A intersection B. Sorry, the probability of A intersection B. So here we can use probability of A intersection B is probability of B given A into probability of A. So probability of B given A is given, it is 0.5, and probability of A is 0.6. So you get 0.3. 0.0. Point. Then, then in the lecture, there is some discussion on Bayes' theorem. So this theorem, this is about updating belief. So it's like we start with a certain belief about something, and then we see some evidence, and then we update our belief. So this is how this Bayes' theorem works, and it is given by this expression probability of uh, y given x is equal to probability of x given y into probability of y by probability of x. And now this is the likelihood, and this is the prior, and this is the evidence, and this is the posterior. Now what each of this mean is, uh, prior probability is what you believe before seeing the evidence. That is the prior probability, and likelihood is how likely the observed evidence is, assuming that something is true. And evidence is the overall probability of seeing something, and it is also like a normalization constant. And posterior probability is updated belief after uh, seeing the evidence. That's the question.
Excuse me, ma'am.
Yeah.
Uh, Here, probability of y upon x represent conditional probability or something else?
Uh, yeah, this part is conditional probability. So this is like, you have some belief about something. You have some given data, that is the X, and you want to know, given this has happened, what is the probability that Y will happen. It's a conditional probability in the left side, probability of Y given X. And that is called as the posterior probability. Yeah. So this probability of Y given X, this is the posterior probability. And this is the normalization constant, or it is also called as marginal likelihood or evidence. And this is the prior. So this is what you believe before seeing a new evidence. It's like asking, before any test, what is the chance that a person has a certain disease? Now, likelihood is, if a person has a certain disease, how likely is that the test is positive? It's like, how likely the observed evidence is, assuming that it is, assuming that something you have, uh, something that has happened is true, or your hypothesis is true. So that is the likelihood. Like, if a person has a disease, how likely is that the test is positive? So this is the Bayes theorem, where you start with some belief, some prior probability, and then you update your belief based on seeing the evidence. And so this is the Bayes theorem. Now I'll ask one question on Bayes theorem, one practice question. So there is a machine A, and there is also a machine B. Machine A makes 60 percentage of items for which there is a defect rate of 2 percentage, and machine B makes 40 percentage of the items for which there is a defect rate of 5 percentage. So an item is taken and it is defective. What is the probability that it came from machine B? So there are two machines, A and B, and A produces 60 percentage of the items, B produces 40. The defect rate for A is 2 and for B it is 5. What is the probability that if if an item is taken and it is defective, then what is the probability that it came from machine B? So we can denote an item being defective is uh, by the random variable D, and we can denote uh, an item came from machine B as B. Then what you have to find here is, given you took an item and that item is defective, what is the probability that it came from machine B? So this is what we have to find. Given an item that you have taken is defective, what is the probability that the item came from machine B? Now you just have to apply the formula. Probability of B given D is given by D given B into B by probability of D. Now this is the prior, and this is given by 0.40. Machine B produces 40% of the item. So this is 0.40. This is the normalization constant, and this is given by, so this is the probability of defective item. So defective item can come from machine A or machine B. Now, what is this probability is how many items in machine B are defective plus how many items in machine A are defective. So it's like when, so 60% of the items are produced by machine A, and out of this 60%, 2% are defective. So it is 0.02 plus when you take machine B, 40% of the items are defective, and of this 5% are 40% of the items are produced by B, and of this 5% are defective. Now, probability of T given B is 5%. So, given uh, the probability that an item that came from machine B is defective is 5%. So, that is 0.05. Now, when you substitute, you get 0.05 into 0.40 divided by 0.02 into 0.60 plus 0.05 into 0.40. So you should get a value of 0.625. Okay. Now, so this is about Bayes' theorem. Then coming to another topic that is discussed quickly, I'll go through this expectation variance, and then we will discuss the last year assignment questions. So the expectation is for a random variable x, the expectation is given by so for different values that x can take, we take the uh, sum of product of x and its probability. So that is the expected value or the mean or the average. So this has some property. One property is that expectation is linear. That is, if x is a random variable, any function of x is also a random variable, then in that case, so if x is this random variable, then when we say expectation is linear, what we mean is when I have x as a random variable, and when we are asked to find expectation of ax plus b, then we can get this expression. So a times expectation of x plus b for all a and b that belongs to real number. This is one property of expectation. And another property is that when we want to take the sum, expectation of x1 plus expectation of x2 plus x3 plus etc. up to xn, the expectation of sum of random variables it is equal to expectation of x1 plus expectation of x2 plus etc. up to expectation of xn. So these are two properties of random expectation of a random variable. Now, another important topic that is discussed is the variance. So, variance is it tells you how much the values of the random variable change with respect to the mean, the spread of the distribution. So, so it can happen that, so as Sir explains in the video, like when there are two vector like 13, 13, 13 or 11, sorry, 12, 13, 14. I hope people who watched video will remember this. So when you take these two distribution, in both cases you have the mean 13, but then the variance, the spread is different. Here the spread is 0, but then here it's a non-zero distribution. So this is where the variance is. So it tells you how much the values of the random variable change from the mean value. So this is variance, and the variance also has some interesting property. One is, so first to the explanation of variance. So variance is given by expectation of x minus mu whole square, and this is given by expectation of x square minus expectation of x the whole square. So maybe now this may seem uh, like very abstract, but then when we do some example question, you will feel that, oh, it's nothing. So some properties of variance. So variance is not a linear operator, because when you take this property, so when you have a random variable x, and when you have to find variance of ax plus b, it becomes a square times variance of x. But then when you want to find the variance of x1 plus x2 plus etc. up to xn, it kind of works similar to expectation. So this is an important property where variance of ax plus b is a square into the variance of x. And here the expectation of ax plus b is a times expectation of x plus b. Now, when it comes to covariance, so covariance tells how two different random variables vary each other, whether they are whether when one is increasing, the other is also increasing, or when one is increasing, the other is decreasing. So it will help us to look into such aspects, how two random variables vary together. For example, the height of a person and is the random variable x, and the weight of a person is the random variable y. So it asks about when height of a person changes, how does the weight of the person changes? It varies together. When one increases, the other also increases. Then you say it's a positive covariance value. If it is not, if it's the other way, then you get some negative covariance value. So it tells you about how two random variables vary each other. Now it also has some interesting property. One is this thing where if you have covariance of uh, ax, then it's similar to variance. You will get a square into the covariance. So if I represent the covariance as c, then this is a square into c, where c is the covariance. So we'll do some examples. So these three properties are important. There's a example question in there. Yeah. So this is from previous year assignment problems. So there is a discrete random variable x and it has the following probability distribution. X is equal to 1 with probability 0.2, x is equal to 2 with probability 0.3, 3 with probability 0.3 and 4 with probability 2. You are asked to find the expectation of x and the variance of x. Yeah. So, first question is about expectation of x, and this is given by the formula x into p of x, and and p of x values are given here. So, x can take value 1, 2, 3, and 4. And each of this value has a certain probability. 1 has zero point 0.2, 2 has zero point 0.3, 3 has zero point 0.3, 4 has zero point 0.2. So you multiply that. So when x is 1, the probability is zero point 0.2. When x is 2, the probability is zero point 0.3. When x is 3, the probability is zero point 0.3. When x is 4, the probability is zero point 0.2. So this will give you 2.5. So this is the expectation of x. Now, the variance of x is given by expectation of x square minus expectation of x the whole square. So, expectation of x square is sigma x square p of x, and this is whatever we got here, the square of that. So here you just have to square the values of x. So it is 1 square into 0 0.2 plus 2 square into 0 0.3 plus 3 square into 0 0.3 plus 4 square into 0 0.2 minus 2.5 the whole square. So when you do this part, you get around 7.3. So the variance of x is 1.05. Now you go to the practice question, the previous year assignment questions. So there are three events A, B, and C such that A and B are independent, B and C are disjoint. Given probability of A union B is 0.4, B union C is 0.5, A is 0.2, find P of C. Yeah. So when A and B are independent, that means probability of A intersection B is equal to probability of A into probability of B. And when B and C are disjoint, that means probability of B intersection C is 0. This means they are mutually exclusive events. That means they will not happen simultaneously. They will not occur together. But then independence means that two events can occur together, but then they may not be related at all. No relation. But this mutually exclusive means when they don't happen together. So using these two properties, you can calculate probability of C. So you have probability of A known. We don't know what is probability of B. So first we have to find probability of B. So probability of B is equal to A union B is 0.4. Probability of A is 0.2, and it's given A and B are independent. So A intersection B will be A into B. So it is 0.2 into probability of B. So you take to this side, you get 0.8. Probability of B is equal to 0.2. So you get probability of B as 1 by 4.25. Now once we have this, probability of B union C is probability of B plus probability of C minus probability of B intersection C. B is 0.25. C we don't know. B union C is 0.5 given. And B intersection C, B and C are disjoint. So it is 0. Therefore, probability of C is 0.5 minus 0.25. 0.25 is the answer. Next question. Using the information given in the previous question and the fact that probability of A intersection C is 0.15, find A union B union C. So the formula for A union B union C is probability of A plus probability of B plus probability of C minus A intersection B minus A intersection C minus B intersection C plus A intersection B intersection C. B intersection C is 0 because B and C are disjoint, and here also B intersection C, so it is 0. So you have only this part A plus B plus C minus A intersection B and A intersection C. And this A intersection C is given to be 0.15 here, and A intersection B we have here. A and B are independent, so A intersection B is 0.2 into 0.25. C is 0.25 we found, B is 0.25 we found, A is 0.2. So when you substitute, you get 0.5. I hope that is clear. I have a question that is similar. So suppose probability of G is equal to zero point 0.8. Probability of K complement. So G and K are two random variable. Probability of K complement is equal to 0.3 and probability of G and K is 0.6. Question is, are G and K independent? Yeah, they are not. Then what is probability of G intersection K? That is 0.6. Yeah. So probability of G intersection K is given to be 0.6 and to show that G and K are independent, this should be equal to probability of G into probability of K. And the only part that is tricky is this. So probability of K complement is given. So to get probability of K, you have to do 1 minus this complement, which is 0.7. And then, so 0.7 into 0.8, you get 0.56, which is not equal to zero point 0.6. We'll do this one. So the question here is, you have two random variables, x and y, and their PDF, their probability density function is given here. So it can take a value, a triangular distribution like this from -1 to 1, and this can take a value, a triangular distribution from minus zero point 0.5 to 5 y value. So the question is, which of the following is not a sample xy that can be drawn from the joint distribution of these two random variables? So is x is equal to 0.1 and y is equal to 0.4? Is it possible? X is equal to minus 0.4, y is equal to minus 0.1. Is it possible? X is equal to 0.25, y is equal to minus 0.75. Is it possible? X is equal to 0.75, y is equal to minus 0.25. Is it possible? Yeah. So the correct answer is C. X is equal to 0.25 and y is equal to minus 0.75 because y can take a value for this PDF between minus zero point 0.5 and zero point 0.5. So minus 0.75 is a value that is outside. So y is less than this minus zero point 0.5 value cannot be sampled. So the answer is 0.25 minus 0.75. Next question is, if the two random variables x and y are independent, which of the following samples xy is most likely to come from their joint distribution? So, uh, you imagine that the x and y are independent and which of the following samples? So whether is 0, 0 more likely to occur than 1, 0 or 0, 1 or 1, 1? What is the sample that is most likely to occur? Yeah, so it is 0, 0. So if you have understood what a probability density function means, you will be able to answer this. So it tells you about what is the chance that a certain random variable, what is the probability that a certain random variable can take a certain value, and it tells you how likely you are to be, how likely the random variable is to be in a certain state. So when x is equal to 0 and when y is equal to 0, you can see that. So this is when x is equal to 0 and y is equal to 0. So when x is equal to 0, the PDF is maximum. When y is equal to 0, the PDF is maximum here. So you get the maximum probability with this. And this is the most likely outcome. So this is the maximum, or this is the highly likely outcome, or the sample that can come. So when you randomly, so you have a set of, you have a box full of certain kind of balls, say red and blue. And if there are more number of red balls, there is a highly likely chance that you get a red ball. So it is something similar to that when you get x is equal to 0 and y is equal to 0, there is a maximum, the probability, the probability density function is maximum at that point. So there is a that is the point or the sample with the most likely to be drawn. Next question 7. In a study of 1000 patients, 400 patients have hypertension, 600 patients have diabetes. Among the hypertensive patients, 250 also have diabetes. Let X represent having hypertension. X is 1 if patient has hypertension, X is 0 otherwise. Y represent having diabetes. Y is 1 if patient has diabetes, Y is 0 otherwise. Find the conditional probability Y is equal to 1 given X is equal to 1. So here you have to find probability of Y given X. And this you can find using the total probability, the joint probability, y given y comma x by probability of x. And so y is when the patient has diabetes and x is when the patient has hypertension. So it is mentioned that uh, 400 patients have hypertension, and among the hypertensive patients, 250 also have diabetes. So what is the probability that someone has someone is diabetic as well as he or she has hypertension is 250, because it's mentioned 250 also have diabetes. So that also have diabetes. So that means this 250 also have hypertension. So P of y comma x is 250, and the people who have hypertension is 400. So it is 0.625. Okay. Now question number 8. So there are two random variables x and y, and their joint distribution is given like this. What is the covariance between x and y? So covariance of x comma y is given by expectation of xy minus expectation of x into expectation of y. So this so you have to find each of the marginal distribution. So probability of x is equal to 1, probability of x is equal to 2, probability of y is equal to 1, probability of y is equal to 2, probability of y is equal to 3. I think if you make the table for this, and then write for each of this value, Then probability of x is equal to 1 is this 0.3 plus 0.2 plus 0, which is 0.5. Probability of x is equal to 2 is 0.1 plus 0.2 plus 0.2, which is also 0.5. Probability of x is equal to y is equal to 1 is just summing 0.3 plus 0.1, which is 0.4. Y is equal to 2 is 0.4 again. Y is equal to 3 is 0.2. Now, what we have to find is expectation of x is 1 into 0.5. So this is x is equal to 1 into 0.5, 2 into 0.5, which is 0.5 plus 1, 1.5. Similarly, expectation of y is 1 into zero point 0.4 plus 2 into zero point 0.4 plus 3 into zero point 0.2, which will be about 1.8. Now, so we have expectation of x and expectation of y. Now we have to find expectation of xy. So for this, we take one value of x, so 1 into one value of y, 1 into 0.3. That is 0.3, where did it come from? 1 into 1 into 0.3, 1 into 2 into 0.2, 1 into 3 into 0, 2 into 1 into 0.1, 2 into 2 into zero point 0.2, 2 into 3 into zero point 0.2. So this you have to write, and then finally you get a value of around 2.9. Then the covariance of x is this expectation of xy, which is 2.9 minus 1.5 into 1.8. So it is around 0.2. This is the value you should get. Yeah. So thank you all for attending today's session.